Hey guys, I just got noticed that my wife's coming home today, so we're not having class. But I'm going to record the lecture for you because I have the mental capacity today, and the lecture's a good idea. Here we go. Not sure I want to do that at all. I want to. There we go. I want to find the right button. That's what I want to do. Okay, so today we are looking at both sections 5.3 and 5.4. I'll try to slow down my speech, but I'm a little excited. A little excited. First of all, today is Veterans Day. If you are a veteran, there are free Dunkin' Donuts today. Just make sure you have an ID. For all former and current military members, if you have served in the U.S. military, thank you very much. If you have served in other militaries that were not against the United States, thank you for your service there too. I'm guessing if you were in the military that fought against the U.S., you're not in my class. But even if you're not in my class, thank you, veterans, and thank you for sharing your loved ones if you are the dependent of a military affiliate, a military person as well. Wow, I lost my thoughts. Here we go. Section 5.3 is what we should have talked about on Wednesday. And in 5.3, there's two important concepts here. I mean, there's inverses, but you did inverses in pre-cal, right? We've done inverses in college algebra, intermediate algebra. If you need to review that, go ahead and review it, but I'm not going to cover it in calculus. Monotonicity. Mono means one, and tonicity, it's like a tonal, it's a pattern, right? Pattern of speech. So one pattern. In the case of mathematics, a monotonic function is either always increasing or always decreasing. Now, we know this is important to determine if a function is one-to-one because as only one-to-one functions have inverses. So how do we know if a function is monotonic? Keep in mind if the function is always increasing, the derivative will always be positive. I don't know what I did there, so I'm going to erase it. But if the function is always decreasing, the derivative will always be negative. So all we have to do is check the derivative. Let's look at some examples. Consider the following function. Let's find the derivative. Just a little polynomial. That's 3x squared minus 27. That's not true. Let's find a derivative. Minus 54x plus 243. Okay, so that's my derivative. No big deal. But is this always positive? We could graph this on our graphing things, but we're also pretty intelligent people. If we look at the vertex, 54 divided by 2 times 3, that's 54 divided by 6, which is 9. The y-coordinate, f prime at 9, let me see, 9 squared is 81. 81 times 3, 243. All right, so that balances out. 54 times 9, 5 times 9 is 45. 450 plus 36. This is negative 486. So my vertex is at 9, negative 486. For this parabola, right? For the derivative. So my graph is going to look something like this. Way down here. We know it opens up. So we know part of the time the derivative is positive, part of the time the derivative is negative, and therefore it's not strictly monotonic. All right? Because sometimes the derivative is negative, and sometimes the derivative is positive. If my vertex was above the axis and the parabola was opening up, it'd be always positive. If my vertex was down here and the parabola opened downward, then it'd always be negative. It's monotonic. But this parabola is both positive and negative. Therefore, the derivative is both positive and negative. Therefore, it's not strictly monotonic. All right. Find the derivative of cosine of 5/8 x. So f prime of x, the derivative of cosine is negative sine. the leave the inside alone. And then we'll multiply by the derivative of the inside. So I'd write this as negative 5/8 sine of 5x over 8. But I happen to know that the sine function is both positive and negative. So this one is not strictly monotonic either. But that's all we're looking for. All right. Once you find the derivative, is the derivative always positive or always negative? No, then it's not strictly monotonic. So what happens if we know a function's monotonic? All right, we're going to take a look on a restricted interval. Once we find a function whose derivative is always positive or always negative, right? And there are examples in the homework. We don't actually have to know what the inverse is to evaluate the derivative at a point. Check out this theorem. And remember, we're using Larson, so I want to make sure I give Larson Calculus, 11th edition, all the credit because I did not write this. Let f be a function that is differentiable on an interval I. If f has an inverse function g, so if f is monotonic, then g is differentiable at any x for which the derivative at g of x is non-zero. In fact, okay, remember, g is the inverse. So what this actually says is f inverse derivative at x is the reciprocal, the derivative of the original function evaluated at that inverse point. All right, here we go. So we're going to use the function f and the given real number a to find f inverse prime at a. Okay, here we go. F of x is cosine of x. So what I know is I need to know a few things. First of all, if a equals 1, I am looking for f inverse prime at 1, which is 1 over f prime at f inverse of 1. Okay, so let's unwrap this. F of x is cosine of 6x. Now, f inverse of 1 equals b means that f of b equals 1. So I want to know for what value is cosine of 6b equal to 1. Well, in this interval, right, we're right here in the first quadrant, just really, really small in the first quadrant. I know that the cosine is 1 when my angle is equal to 0. So my b value is 0, right? Cosine is equal to 1 in this interval at a value of 0. All right, cosine of 0 is 1. So I know that 6b has to be 0, so that's a b. My b is equal to 6. That is not a 6 is equal to 0. That's weird. So really what I'm looking at the point here is I have a point for f that is 0, 1. Right? Put in 0, we get 1 out. But in our function, what we're looking for is now 1 over the derivative at 0. The derivative of the original function. So if this is our original function, and I'm trying to keep it all on one page for some strange reason, my derivative of cosine of 6x, derivative of cosine is minus sine. Leave the inside alone. Multiply by the derivative of the inside. I like to write that better as minus 6 sine of 6x. And at 0, the sine is 0. Oh, that's 1 over 0. Are you kidding me? I'm going to pick better examples when I randomly decide to give you guys an example. This does not exist. We picked the one value that was going to give us a 0 in our denominator. That sucked. So let's do it again. Oh, I didn't do it again. I only did one of those. It happened to be a bum example, but the rest of them should work out for you. While we're here, I'm going to hit save. Make sure we keep those. Now, I did that entire section in 10 minutes. Don't forget, you have rewind, you have pause, and I've also posted these notes on Blackboard by the time you're watching this video. All right, so I want to talk about 5.4 as well, exponential functions. We're super fortunate that these are not large concept sections. The actual concepts of them are pretty straightforward. Doesn't make them easy, right? But it makes them easier than a lot of the stuff that we've done in chapter 3 and 4. So section 5.4 is exponential functions, I believe derivatives. Oh no, derivatives and integrals. So let u be a differentiable function of x. The derivative of e to the x is e to the x. It's itself. And the only thing we have to do if there's something going on in the exponent, right, we use a u substitution. So it's itself times the derivative of the exponent. So e to the u times the derivative of the exponent. So, and nice little remark here. Let's find the derivatives. We got some product rule going on here. So we'll take a look at those individually, but here we go. Our derivative is, so we'll have first, derivative of second, plus second, derivative of the first. Minus, and since it's a minus and I have a product rule, I'm going to put it all in parentheses. First, derivative of the second, plus second, derivative of the first. And of course we have plus, leave that coefficient of 7, the derivative of e to the x is itself. All right, notice each time, let me use a different thing here. Each time we have a copy of the original inside the derivative. That's one of the things about the e to the x that we need to pay attention to, is that you should always have a copy of the original in the derivative. As long as there's nothing going on in the exponent itself, it'll be exactly like what we're originally taking the derivative of, whether it's quotient, product rule, even in chain rule, it looks a little the same. All right, that's it. We're done. Moving on, we type it in, maybe sort the order of things a little bit, but it's all good. So let's find the equation of a tangent line to the graph of the function at the given point. We know, as soon as we see tangent line, we know that the slope is the derivative at the point 0, 0. So let's do it. Let's find the derivative. That 3 stays there. The derivative of a natural log is the derivative of the inside divided by the inside. All right, so the inside stays the same right there. And here, right, because it's a log, I'm looking at the derivative of the inside. All right, so the derivative of the inside, I'm going to leave that 1/2 as a coefficient. Instead of using a quotient rule, I'm going to pull a 1/2 out in front. The derivative of e to the x is e to the x. The derivative of e to the negative x is itself times the derivative of the inside. So we see we have this 3 hanging out. These halves cancel out. A half divided by a half, they cancel each other out. I will have e to the x minus e to the negative x all over e to the x plus e to the negative x. All right, so this is our derivative. And so when we evaluate at an x value of 0, we'll end up with 3 times e to the 0 minus e to the 0, make sure that's a minus sign, over e to the 0 plus e to the 0. Now we know anything other than 0 raised to the 0 power is 1. So this is 3 times 0. Are you serious? 3 times 0 over 2. That's very zero in my world. There's no way this is correct. There's no way this is correct. So I'm going to pull it up and take a look. 5.4, number 7. Look, I posted the notes. 5.4, number 7. It can't be that simple, right? Y equals 0. There's something very unsettling about doing all that work and having it come out to be 0. So remember, this is our slope m. We'll have y minus 0 equals 0 slope times x minus 0 because we have this point. I'm sorry. I should have picked a better problem. But it's, derivatives with e to the x. It's pretty very, very straightforward. Sorry. The good news, since the derivative of e to the x is itself, the integral of e to the x is also itself, plus a c. And the great news is, even with a substitution, e to the u, it's just e to the u. The antiderivative of e to the u is e to the u plus c. Always remember a capital C for the constant of integration. So we're going to let u be 7x minus 2. Then the derivative of u is 7dx, but I don't have an extra 7 hanging out. So this is 1/7 du equals dx. So my integral of e to the 7x minus 2 dx, I have a sneeze coming, so I apologize if it happens without me noticing or catching it. It's coming. It's 1/7 integral of e to the u du, which is 1/7 e to the u plus c, and we reverse our substitution. Remember, we always substitute twice. This is 1/7 e to the 7x minus 2 plus c. And remember, the cool thing about math is that you can check your answer, right? Find the derivative of this. We know how, we just did them. It's e to the 7x minus 2. We get our integrand back again. This is the last problem that I decided to put on the lecture. I knew it was going to be a short lecture. I'm a little excited, and I'm talking fast. I can't imagine how many more of these I could have done. All right. Let's see. I would probably do this. I would look at 8 over e to the 7x dx minus the integral of e to the x over e to the 7x dx, because this is the integral of 8 e to the negative 7x dx. We don't have to do like a u equals e to the 7x, some kind of natural log thing happening here. No, we have negative exponents. We could totally do that. And if I have e to the x over e to the 7x, that's e to the negative 6x dx. So I'm going to use substitution twice here. We'll end up with 8 times. All right, let's put it over here. The integral of e to the negative 7x dx, I'm going to let u be negative 7x. du is negative 7 dx. So, of course, I don't have that negative 7, so I have to divide on the other side. So this is 8 times a negative 1/7 e to the u, and we're going to have a plus c. All right. We also have, let's go purple, the integral of e to the negative 6x dx. If u is negative 6x, du is negative 6 dx, right? We don't have that, that negative 6, so it comes to the other side in the form of a negative 1/6. And then the integral of, I'm going to have to go up on this one. Negative 1/6 integral of e to the u du. So I'll have e to the u plus c. And we're going to just put a big old giant circle around this whole thing. And as I'm typing it in, I would not add any extra space or anything. But you can see you could do all these little integrals using a simple substitution. And then you've done something that looks complicated, but it's not. And this is why we're heroes on campus, is because we look at this and we can understand it and we can solve it. Heroes, geeks, it depends on your point of view, whatever. Remember, you're my 1%ers. You're doing awesome. Keep it up. I'm sorry I'm not going to be there today, but we got a video and my wife is coming home. I miss you guys. To be honest, I'm not. We're going to do this remote next week as well. She's still on quarantine until the 19th. She can't get tested until that date. And since she can't get tested and she is going to be in the home, I'm not risking you guys. I'm not risking anyone. I don't have any symptoms. My daughter doesn't have any symptoms. My wife will be masked in the house. I'm still not taking any chances. I'll see you after Thanksgiving. Pay attention to Blackboard. I'll be sending announcements. I'll make this official. And I will see you again before finals week. I promise. I'll be back. I'm not ready yet. I need a minute. Miss you guys. Bye.